So welcome back, everyone. So you get me again today. So in this lecture, what I want to do is I want to continue from where we left off this morning. And what I want to do is I want to talk about accelerator-based probes for dark photons, and then also for a model where we have the dark photon interact with dark matter, and then see how we can probe light dark matter with accelerators. And to begin, I first want to talk about the decays. So to start with, we have the dark matter heavy. We imagine that it's not part of the thing right now, and we just want to consider pure dark photon. And we left off this morning where we had this first region where the dark photon is above twice the electron mass, which allows the dark photon to decay to electron and positrons, which are the lightest charged fermions in the standard model, electrically charged fermions in the standard model. In this case, we wrote down the decay width, which is given by this. Okay. So now, before we work out the lifetime based on this, there's of course other channels that are available depending on the mass of the dark photon. So if I make it heavier, then it could potentially decay into other things. So what's the next heaviest fermion that it could decay to? There was some mumbling here. Muons? Okay. Okay, muons. Okay, so for muons, it's actually very similar. It's basically just equal to the E plus E minus formula with ME replaced by MU. And the same for tau. Okay, but there's a little bit of a challenge because we know that there's many other possible hadronic states as well. Okay, mesons and so on that it could decay to. And we have to figure out how to write the decay width for this. So what we can do to do that is we can use the fact that hadrons, the decay width to hadrons, I'll say in a second most precisely which ones I mean, is the decay width to mu plus U minus times something that's called the ratio R, where the ratio R is defined to be the cross-section of E plus E minus to hadrons divided by the cross-section for E plus E minus to mu plus U minus. And this is just through a standard model process. So in the standard model, you can light E plus E minus pairs. There's a photon at low energies. There's also Z, but at low energies is basically the photon. And that can produce standard model particles. Let me keep the same notation, FF bar. And as you increase the beam energies of electron positrons, you can see what type of final states open up. So first the E plus E minus, then the mu plus E minus, then you've got pi plus pi minus, pi plus pi minus pi 0. And you see various resonances in the spectrum. So when you do this, and you plot this as a function of root S, so the center of mass energy squared, and I'm going to try and produce a plot here. Let's see how successful I am. So you've got these resonances. There's the W and the omega, and there's a phi resonance, and then it increases, and at some point you've got the Z resonance, etc. So this is the Z. This is the this is about 3 GeV. This is 1 GeV. Then we've got here the below 1 GeV, around 700-800 MeV. And we've got here the omega, there's the rho, there's the phi. At 10 GeV, there's the upsilon. There's the J psi. Something like this, okay? And this is the Z, of course. And you see all these different resonances. And we can just use that data, basically, to estimate what the decay width is for dark photons, because the dark photon comes about just from this kinetic mixing with the photon. Okay, so this is a useful way to write this. And this is basically based on data. If you want, you can look this up in the PDG or elsewhere. And this way, we can write down the total width of the dark photon by just summing everything up. So what we get then is the following. So so we can write down, so let's write down not gamma, the total width, but just the decay lifetime, okay, c tau. Decay length, I should say, sorry, multiplied by c. And that's just proportional to 1 over gamma, appropriately normalized with factors of c, etc. And what we get is that this is about 0.1 centimeter for an epsilon of 10 to the minus 5 for a mass of a GeV times some factor, which I'll here call N effective, which has nothing to do with cosmological N effective, just to confuse you. But the N effective here is just the number of available states that the dark photon can decay to. So it's basically going to be given by the sum of electrons and muons. So let me write it the following way, and then I'll explain what it is. So 1 minus 4 ml squared prime squared. So this basically sums up all these additional factors which come from phase space, which depend on what particles, how heavy the dark photon is, and what it can decay to. So here we're summing over electrons and tau. The muon sum is contained in here with the first term, and then the times R is basically the muon cross-section, times hadrons over muon. So that's just basically the hadron contribution. And then the R that you take is you just evaluate it at the appropriate dark photon mass. Okay. And this then tells you, okay, yeah, let me stop here for a second. Okay, so again, those are basically phase space factors. You see that if the dark photon mass is less than twice the electron mass, this doesn't work. Okay, it's a negative number, imaginary number then. So of course the dark photon has to be above the lepton mass to be included. But as you dial up the dark photon mass, you get different contributions. And before I talk a little bit more about the decay lengths involved here, let me just draw the plot of the branching ratio then of the dark photon as a function of mass to the different standard model particles. So, let me put 1 here, down here 0, somewhere there's 0.5, in the middle there, and we start at 2 ME. And at 2 ME, the branching ratio is completely into electrons. Okay, so it starts out, there's a small increase, small threshold behavior, but then it basically is 1, just purely into electrons. And then there, once you're above the muon channel, so 2 muons, what's the mass of the muon? Okay, 105 MeV, so 2 times that is 210 MeV. Mass of the electron is about half an MeV, so this is 1 MeV. So 1 MeV and above, this plot starts at 1 MeV, and then as you increase, the branching ratio will drop. Eventually, above the muon threshold, the branching ratio to mu plus mu minus will turn on. And let me see how badly my skills turn out to be. At the same time, a little bit above the muon threshold, the R, so you're actually able to produce pi plus pi minus. So the pion has about 135 MeV mass. So above that, you're actually able to start putting some pions in. Oh, I've got color. Let me use color. Excellent. Okay, good. And then Yellow, let me know if this is not visible. I think it should be. And then let me finish my electron lines, etc. So the electrons and muons basically overlap. So this is mu plus or minus. This is pi plus, pi minus. And yellow is pi plus, pi minus, pi 0. This is 800 MeV, approximately. And this is the pi plus and minus is basically the row resonance. So E plus E minus is going to rho decaying to pi plus pi minus. And the pi plus pi minus pi 0 is the omega resonance, which is very narrow. The pion resonance is very, the row resonance, sorry, is very broad. So this is the branching ratio. What else do I want to say about this? I think that's it. Okay, so let me just write here. This is from the omega, and this is from the rho. So you see that just above the muon electron threshold, you've got just decays purely to E plus E minus. Once the muons are allowed, once you're heavier than twice the muon mass, you can also decay to mu plus E minus. There's some threshold effect, but then the E plus E minus and mu plus E minus are just the same, which you can see from the formula as well. And then you have got these hadronic things, pi plus or minus, and pi plus or minus pi 0 that come in as well. And of course, you can keep going up in mass. Okay. But we'll care about this low mass. Okay, questions on this? Yeah.
Why does the curve for E plus E minus start going up again?
So the hadronic contribution decrease. So this is a branching ratio plot, not a gamma, right? Okay. Not the width. So the branching ratio is the width to E plus E minus divided by the total width. So what happens if the total width changes? Okay. So once you hit these resonances, which are pretty broad and large, which you can see from the R plot as well here, you prefer to go to these hadronic states, which means just the branching ratio of going to E plus E minus is smaller, even though the width doesn't change that much as you scan over this. The width to E plus E minus. Okay. Okay, so with this knowledge, we can now ask how can we produce this and how can we see it? So there's many ways to produce it and many ways to potentially see it. One thing I want to just point out, so there's the C tau formula. And what you can see is that depending on what epsilon is, and also the dark photon mass, but it goes to epsilon squared here, you can get very different lifetimes of the dark photon. So if epsilon is smallish, 10 to the minus 3 or so, you get very quick decays, which you basically can't resolve. I mean, they're prompt decays. Okay. When you at epsilon 10 to the minus 5 or so, there's a small displaced vertex which you might hope to resolve. Okay, so you can look for a displaced vertex. So that dark photon moves a little bit, it's invisible of course, and then decays to E plus E minus, so there's a little vertex that appears out of thin air, if you like. Okay, so I'll talk more about that in a minute. And then if you go to smaller epsilon, the thing becomes very long-lived. Okay, and it can go for a long, long time before it decays. So you want to have different strategies, even just in this very simple model, you want to have different strategies for trying to find such a particle. And the following is a collection of strategies, and I should say they're not just applicable for the dark photon, but in many other ways that you might want to produce a dark sector. So it's just good to know about them, sort of what the available options are. So if you have a model, in future you might think about how it is really constrained or how it might be constrained with additional experiments. Oh, I'm sorry, and I forgot number 2. This is quick, so let me just say this. So there was a second region where it was below twice the electron mass. And this case, as already indicated this morning, is going to decay through loop to 3 photons, because there's no electrically charged states available, and the electron is flowing this loop. And this decay lifetime goes as 1 second for an epsilon of 0.003. And it has a very high power with a mass of A prime, so to the 9th power. So this comes from all the propagators in here, the loop momenta, etc. So roughly what you get is this. And if you want to know the exact calculation of this diagram, so this was actually done by McDermott, Patel, and Ramani in 2017 in this paper here. But for us, we're not going to worry about this right now. What you can see is that for an epsilon of 3 times 10 to the minus 3 and a dark photon close to the electron mass, this doesn't include threshold effects. If you want to know about them, you can include this. You can look at that paper. But basically, you're just close to the electron mass, but where you don't have to worry about threshold effects, this is already 1 second. So if you make the dark photon mass a factor of 10 smaller than the electron mass, you get this factor of 1 over 10 to the 9. Okay, it's a huge suppression already. And the thing will easily, which then is a factor of 10 to the 9 in the numerator, right? And this thing will easily become long-lived very fast. And it can easily live longer than the age of the universe. And that actually makes it a viable dark matter candidate. So the dark photon itself, it's a boson, remember, and here we're sitting at below an MeV, but now you can just take it down to arbitrary small masses. That's actually a good dark matter candidate down to arbitrary small masses. Okay. And it's easily long-lived. It can easily live longer than the age of the universe. Okay, so that's a region that's interesting, but, well, that's all I have to say about it. Okay. Questions on that?
Yeah, I have one. Where does the branching ratio go down before the opening of the given channel? I understand it falls from the transition. It's not obvious.
Yeah, that's a good point. That's because I can't draw. You're absolutely right. Thanks, yeah. Anyway, you know what I mean. Yeah, thanks. Yeah, no, that's an important point. Thanks. That violates physics. Okay. Okay, other questions? Other corrections? Okay, good. Okay, so let's go through some examples. And the basic idea, and so we'll focus on, right, heavy-ish, so above this threshold. And the basic idea is that whenever there's a photon, you can also have a dark photon. Okay, so we can go through all the ways of producing photons. So since we're interested in low energy, low mass particles, it turns out that E plus E minus colliders are a good thing to use. And in particular, the way we can produce a dark photon is as follows. So this is how we can produce 2 photons. All right, that happens very often at an E plus E minus collider. And I can just take one of these gamma and replace it with a dark photon. Okay, that's how I can produce a dark photon. And the cross-section for this will scale as 2 pi epsilon squared alpha squared over the center mass energy squared. And then there's some factors which take care of the kinematics. And then there's also some large logarithm which depends on the exact setup. Let me say a word about that in a second. But what you see is that, first of all, it goes as epsilon squared. That's not surprising, just because the coupling here is epsilon times the electric charge times E. So in the amplitude, I have got this. In the cross-section, I square that, so I've got an epsilon squared times an alpha, basically. And then the pi's have to take care of themselves. And there's another photon here where I get the other alpha from. Okay, so there's going to be an alpha squared there. And then the energy of relevance, at least if you have low dark photon masses compared to the center mass energy, is just the center mass energy. So just from dimensional analysis, again, you know this has to go as 1 over the center mass energy squared. Okay, and then, of course, when you do get close to the center mass energy for the dark photon mass, if the dark photon mass gets close to that, then you will get a suppression as well, because there's a penalty for producing it. So that's this factor there. And then there's a logarithm which you get from enhancement when the photon is collinear with the positron or the electron. So that's just some log which I'm not going to worry more about. But I'll just say here from gamma collinear with electron or positron. And you can look at more details if you want. So I'll give some references throughout this just for completeness. And if you are interested, you can look more at this. Okay. And then we can put some numbers in. Okay, so a cross-section is measured in bonds, right, centimeters squared. And then in this case, the thing that's of relevance is a little bit of a barn, so it's a femtobarn here. And for an epsilon of 10 to the minus 3, we get 2.4 femtobarn, assuming a center of mass energy of 10.58. And then times some log. Okay. Which you can think of as a number that's 1 to 10. Okay, so it's not that important. And what you see here is, so first of all, let's talk about some of these numbers a little bit. The main thing is this dependence of 1 over center of mass energy squared. So that tells you that low energy colliders are good. High energy colliders are not so good to looking for this, to producing this. Okay, so you don't want to go to, so what you want to do is you want to go to the low energy colliders, low energy E plus E minus colliders. You don't want to go to LAP or some future E plus E minus collider. You like the low energy colliders. Yeah.
Yeah, so I just have a quick question. Because since this A prime is massive, then why do we need this associated production with the photon? Why can't we just have an E plus E minus going to this A prime?
So you could do that, it's an on-shell A prime, right? But then you need to tune the beam energy to really get it on shell.
Right.
So you could do that and you can scan.
Right.
But often,
like you do for the Z, for example.
Right, so if you could do that, that's good. But it's not easy to change the beam energy always and scan very finely. And the problem here is that the dark photon, the width is tiny. So the Z is pretty broad. It's a 2 GeV or something, right? It's order GeV. This is going to be very, very small width. So you've got to basically you can't fix your energy. You've got to tune it by like kV energies ideally. Right. Scan by kV energies depending on this.
For an E plus E minus collider, that's
it's hard to do, right? Yeah, yeah. So you can do that a little bit, and if you knew exactly where to look, you would do that and just sit on the resonance and do that. But we have colliders that sit at particular energies already available, and for them it would be this process.
Sure.
Yeah, but you're right. Yeah, so it's a good point. Yeah, thanks. Yeah.
And how often in model building do you actually know exactly where that A prime is sitting in that?
No, yeah, you don't. So it's usually free parameter. Yeah, right. So So the particular I picked here, not completely arbitrarily, 10.58. That seems like a ridiculously precise number to pick for an example, right? But what is that number? What collider has that number? Okay, so those are the B factory. Oh, yeah. So the B factories, things that are called B factories. So this is where the upsilon resonance sits. So this thing that I drew very precisely, right here. That's the upsilon. There's actually several little resonances next to each other. There's upsilon 4s, 3s, 2s. They all sit close to each other. This, I think, is the upsilon 4s. And they want to do that because they want those things decay to B mesons. And they want to study B mesons. That's why they're called B factories. But that's why they pick that energy. Okay. There's other colliders which don't pick 10.58. They want to sit on the phi resonance, for example. And then they have a center mass energy of 1 GeV. So Chloe at Daphne in Italy is an example of this.
Then you assume the number for the mass of this dark photon.
Here I just assume it's much less than the center mass energy squared, so this term is negligible. So in this approximation I just made that this MA prime is much less than ECM.
Okay.
Then there's no mass dependence.
But if you have like this small energy colliders, and then you assume even it's much less than this center of mass energy, isn't it a problem?
Well, no. So if I've got a GeV, right, if I sit at a GeV collider, there's all this parameter space that's potentially of interest. Okay, and of course, if you do a proper experiment, you don't take this approximation. You just calculate it properly, or you simulate it, right? Right. So I'm just saying this is just sort of an estimate to show you some numbers. Okay. Okay. So let me just tell you about these colliders. Let me keep this. So it's good to know about these, I think. Obviously not just for dark photons. So Chloe is a Daphne, it sits at 1 GeV. It has an integrated luminosity of about 2.5 inverse femtobarn. Okay, so does everyone know about integrated luminosity and luminosities? Yeah, okay. Maybe Tao will talk about that more. But okay. Tao, are you going to explain to them integrated luminosities and all that? Oh, you did already? Oh, great, okay. I missed your lecture, I'm sorry. Okay. No, that's great, okay, so why am I asking you? So everyone knows this is great, okay, good. So then there's Baba, there is Bell, there is Lep, and then there's Bell 2. Everything is past except Bell 2, which is near future, very near future. And there's also Chloe 2 now, which I'm not going to write down because I don't quite have the parameters here. But Baba has about 10 GeV. Bell was 10 GeV. So Baba and Bell were B factories. Chloe was a phi factory, sitting on the phi resonance. Lep was 91 GeV, and then it also ran between 189 to 209 GeV. And then Bell 2 is again going to sit on the B meson, on the upsilon resonance, to produce B mesons, and it's about 10 GeV. And the integrated luminosities are, so for Baba and Bell, the combined one is about 1.4 inverse attobarn, or 1,400 inverse femtobarn. Lep was 0.5 on 91, and 2.6 inverse femtobarn in the other mass range. And Bell 2 will be about 50 inverse attobarn, or 50,000 inverse femtobarn. Okay. Now, back in 2009, when these papers were written and dark photons became popular, Baba and Bell had not done these types of searches. Okay. In fact, they didn't do it for quite a few years later, until quite a few years later. And you could see here, if I just put in an epsilon 10 to minus 3 in the center mass energy of Baba or Bell, we have 2.4 femtobarn cross sections, and if you multiply by order 1,000 in this femtobarn, you could have thousands of events sitting here just for this epsilon. And of course, you can go larger than epsilon, which would be even more. Okay, and that's an example where data was already existed, the data was taken already, and where you could have just had lots of these events, which were just lying around, and no one would know that they're there because no one looked. Okay, so that's obviously one of many, many examples, and hopefully, or I'm sure you'll find examples in your career as well, where you have some interesting signal in mind, and it's just not excluded because no one's bothered to look. And that's, I think, one important job as a theorist, to come up with signals that no one's looking for right now, okay, and motivations for looking for those signals. And then tell the experimental colleagues about them, and then hopefully they'll go and look, and hopefully they'll find something, and then you're famous, okay? So, but another important point to make, just to sort of finish this up, this particular section, is that the low energy colliders are really good at this, right? If I go to LEP, you hit both by the center of mass energy squared and also by the integrated luminosity. But of course, if the dark photon mass is heavier than 10.58 GeV, you can't use the Baba or Bell to look for this because it's above the mass threshold, above the energy threshold. And then what you would do, right, you produce this dark photon, and then you would just do what we talked about a few minutes ago, where you would look for E plus E minus, mu plus E minus, pi plus or minus, etc. You would just look at all these final states. Okay, good. So just this simple model, right, is already several PhD years, or student years, I should say, several PhD theses in principle. Okay, it's fun. Okay. Okay. So next, E plus E minus colliders. So the next thing after E plus E minus colliders I want to talk about is electron fixed target or beam dump experiments. So these are also a lot of fun. So in terms of the dark photon context, these papers discuss this. So you're seeing a lot of papers now and also earlier today in 2009. So this is because this whole subject became popular due to dark matter-radiated anomalies, and then due to work by Neil Weiner and Nima Khan-Ahmed and Pospelov and Maxime Pospelov and Adam Ritz and others, which suggested that there's this sub-GeV dark sector, and then people came up with ways to try and probe this. Okay. So this is the idea of a fixed target experiment is that you take an electron beam. So I'm focusing first on electron beams. I'll discuss proton beams in a bit. So you take an electron beam and you shoot it onto some target. And there's different targets you can imagine, right? You can use tungsten or carbon or something. Okay, there's various possible targets you can imagine using. And then you produce the dark photon in the interaction of the electron with the target nuclei. And the way you produce it is through a diagram like this. So here's my target nucleus. Let me call this, well, let me just write nucleus. There's the photon. Here's my electron incoming. And it can radiate a dark photon. And the nucleus, of course, consists of some nucleus with charge Z. Depending on what you use, it's different atomic numbers. So the coupling here, roughly is Z times the electron charge. That's the photon coupling to the nucleus. And and then you can radiate the dark photon like this. So that's one possible diagram. And the cross section for this scales as, well, never mind. So there's some scaling. I'll write down the number. So first of all, the amount of dark photons that you produce here depends on the radiation length, how much target material you have. Okay, so you have a very thick target, then the electron has many, many chances of interacting with the nucleus to produce something. If it's a very thin target, it has less chance. The chance of this happening is characterized by radiation length. Okay, so it's basically the distance over which a high-energy electron, so one radiation length is the distance over which a high-energy electron loses about all of its energy except 1 over E, which is 37%. So it loses most of its energy, 63% or so. And you can consider both thin targets and thick targets, depending on what you want to do. So for one radiation length, the number of dark photons you could produce in such an experiment is about the number, so it's proportional to the number of electrons that you have on target, all right, so Ne. There's an epsilon squared, again because of this vertex here. There's an epsilon here. There's an epsilon E on that vertex there, so there's an epsilon squared. There is Me squared over an Ma prime squared, okay, which is not obvious where it comes from. And then there's factors that depend on the fact that there's one radiation length, and you take everything into account. Very roughly what you get is an order 10 number. Okay. So if you ask what the number of dark photons is that you get is when you have a coulomb of electrons being dumped on the target. So a coulomb of electrons is how many electrons roughly? Yeah, close. Okay, so 6.2 times 10 to the 18. Good. Okay, so for 1 coulomb, and that's a good number. Okay, so that's sort of a good estimate of what a collider can do. So for 1 coulomb of charge, what you get is that the number of dark photons you produce per coulomb is about 10 to the 8 for an epsilon of 10 to the minus 3 squared, and for a dark photon mass of 100 MeV. Okay. So that's a lot. Okay. Now, once you produce it, let's figure out what we want to do with it, right? So you've produced this thing. First of all, it actually turns out that it's produced very forward. It's produced in almost the same direction as the beam, incoming beam. So the typical angle at which you produce it is given by the beam energy, the dark photon mass over the beam energy to the power of 3/2. Okay. And in particular also the A prime carries most of the beam energy. So as this thing comes in, as the electron beam comes in, if it radiates a dark photon, the dark photon gets radiated at high energy, at the beam energy essentially, and very forward, with just a tiny angle deviating from the beam. Okay, so if this is a 20 GeV beam, which is not unreasonable, and the dark photon mass that you care about is 100 MeV, then you've got 0.1 GeV over 20, and then you multiply it to the 3/2. So it's a very small angle. Okay, so these things go very forward. Then, once it's produced, you want to figure out where you put your detector, because the thing is going to decay to E plus E minus, or mu plus E minus, or the various things that we talked about. And you want to know, where should I put my detector? So the other thing to know is that once the thing decays to your fermions, the decay angle of the decay product is going to be of order so it's going to decay to E plus E minus, for example, and the opening angle of these particles, let me make a general FF bar, is going to be given by MA prime over EE. So again, the decay to the E plus E minus pair or mu plus E minus pair that you might produce is very forward in the beam direction. Okay, very small opening angle. So what you want is you want to put a detector very, very forward, that in order to find the dark photon decays. Now, where should you put the detector? So what do you think?
In the material?
In the material? You mean like, where's my target? In here? Okay, why? Okay, so you're saying just make it very close to the thing so that you can have a small, like a wide angle coverage?
If there's a way to somehow.
I mean, so the E plus E minus, of course, or the F plus F minus, they'll just keep traveling, right? You don't need to put the detector close just to catch them. You can put the detector far away, just have vacuum in between. Okay. But okay, so maybe some other ideas or some more comments. Otherwise, I'll just, maybe my question is confusing. I don't know. Yeah, go ahead.
Maybe put a magnet to get the electrons out of the way that didn't track.
Ah, so you want to deflect the electrons that make it through the material without interacting to be not a problem. Okay, so what about the dark photon that decays to E plus E minus right away? Okay. We have a budding experimentalist. Good. Okay. Other things?
Maybe put it just behind the target, like nearly close to the path of the electrons.
How far away?
Depends on the C tau, right?
Good. Okay, so it depends on the C tau. Okay. So anyway, so I just wanted to get you thinking a little bit about this. Otherwise, I'm just talking in front. So it depends on the C tau, right? And you want to put the detector, of course, behind the target. But where you want to put them, it depends on the C tau. In particular, what epsilon is and what dark photon masses you're interested in. So if the epsilon is very small, you want to put the detector far away. And in principle, you can also have a lot of shielding, right? Because the dark photon doesn't care about shielding. It's just going to go straight through. If the decay length is very small, right, if the epsilon is large, then you can't have any shielding because the dark photon is going to decay inside your shield, and that's not good. So you want to have no shielding and have detectors that are able to see the target, the E plus E minus emerge close to the target. So indeed, what you want is a various different detector setups. So depending on lifetime, you want either a thin target, right? What you don't want is so if the thing decays very quickly, if the dark photon decays very quickly, you want the target to be thin because you don't want the A prime to decay inside the target, because once it decays E plus E minus inside the target, those E plus E minus will interact with the same material. And there's something called multiple scattering, which is going to increase the angle randomly and degrade any mass resolution you'll have, which I'll talk about in a second. But for prompt decays, you want to have a very thin target and then detectors that are able to see it. But if the decay lifetime is long, you might as well make the target very thick or have a thick target and a shield behind it, like some dirt, some rocks, whatever, lead, or a mountain, and then look for that. So depending on lifetime, you want either a thin target or a thick target. And the latter we call a beam dump, often. And the former we would call a fixed target experiment. The latter one, you basically dump the whole beam. So the whole beam energy goes into the target, and everything gets absorbed, the whole energy of the beam. Okay. So for prompt decays, so here you want to have an electron coming in. You want to have a very thin target, and then the A prime is produced and basically decays right away to E plus E minus. And then what you want to detect those. So you want to have spectrometers or calorimeters, etc., at the right opening angle. And this opening angle has to be pretty small, so they have to be pretty close. I'm drawing it a very exaggerated way, but you want it to be very close together. This is for looking for prompt decays. So what you want is a 2-arm spectrometer. So a spectrometer, there's 2 different arms, one for the electron, one for the positron that comes out from the decay. There is so just again, so there's of course, so this electron from the beam electron, that's also floating around, but that usually has low energies. Okay, so that's easy to get rid of. You can just measure its energy and you can cut away from it. And there are experiments that have done this and are going to do it. So an experiment that took test run data back in 2010 is called APEX. There's an experiment here at Mainz, I'm not sure exactly where, but somewhere very close by, using the Mainzer microtron, which did an experiment. So MAMI. Very nice data that they took, and I'll mention a bit more about the data in a bit. I'll tell you why it was interesting. So APEX has already taken some data back in 2010, and then this is an experiment at Jefferson Lab, which is one of the national labs in the United States, in Virginia, in the US. MAMI, as I said, is here. APEX will take more data next year, and MAMI is, as far as I know, done. If someone else knows more information, then please let me know, but I think they're done basically with this type of search. And then there's also NA64, which is an experiment at CERN, which uses the electron beam from the SBS at CERN, which is a 100 GeV electron beam. And they also did a search for this type of stuff, basically. This is a very recent result. So just to tell you that I'm not telling you just about papers from 2009. So this came out in March this year. Okay. Yeah.
And do these, do the two arms cover like a large solid angle?
So that's a good point. So usually for Apex and also for mines, for NS64, it's larger as far as I know, but I don't actually know too many of the details. For Apex and mines, it's a very small solid angle. So unfortunately, you have a tiny acceptance. So this beautifully large number that you have of dark photons being produced is actually very small at the end of the day in terms of what you collect. But you can still do something. Okay.
Can you get a handle on where to put them? Like, how would you even estimate where to put them?
Right, so depending on what dark photon masses you're interested in, you want to put the spectrometers at this angle here. Okay, so depending on the beam energy, and the dark photon masses you're interested in, you know what angle you put them in. Or said another way, depending on, in the Apex at Jefferson Lab, these spectrometers are massive, massive objects, okay? You don't just put them arbitrarily where you want them. You have to, it's a big effort to move them. And you can't actually move them closer than 5 degrees, 10 degrees actually, okay? So you can't put them that close, and that determines then what the masses of, what masses you can probe as well, okay? Now, let me just say one thing here. So what's the yeah?
So we'll have a tour of Mommy on the Monday of the work week.
Oh, great. Okay, I won't be here. That's too bad. That's really annoying. Okay, anyway, cool. Yeah, nice. Okay, so now you know. So there's something to ask them about this. Yeah, there's great people here doing this stuff. So one thing is, what are you actually looking for, right? So you're producing these dark photons, and they kg plus E minus, but that's not the only thing that produces E plus E minus pairs. There's a huge background. So the backgrounds come from QED processes, where the electron that comes in can, of course, interact with the target material and produce just electron-positron pairs. So wait, wrong diagram. So one possible process, background process, is this, where you just replace the dark photon with an off-shell gamma. You've got this process here. Another process is where the electron comes in, and you've got this, okay, where this is the plus or minus pair that you produce. Okay, the double line is a nucleus, the target nucleus. And this is a huge, huge process, right? There's no epsilon suppression, okay? So this is a huge process, and you get a lot of E plus E minus pairs. So how are you going to separate the dark photon events from this thing, from this background? And I could have asked the same question for the E plus E minus colliders. And in hindsight, I should have. We could have discussed it then, but I'm doing it now. Okay, how are you going to separate from background?
The angle dependence, maybe if those things have like a...
Yeah, so angular dependence. The other thing you can do, right, you want to select high energy E plus E minus pairs, because you know from the dark photon they have to carry most of the beam energy. So there's cuts like that. That gets rid of a lot of background, but you still have a lot of background. So what else? Yeah. Displaced vertices. So here we're considering prompt decays. Where am I? So displaced vertices is a good point. Once we get there, then the background should not have a displaced vertex. And that's a great way to get rid of background. Very good. I think you were first. Oh, okay. You're ahead of the times, both of you. Okay, go ahead.
In the rest frame of A, they should be back-to-back, whereas in the other case, it's 3-particle final state, so they don't have to be back-to-back.
Yeah, so that's sort of some angular information, right, that you want to use or something. But yeah, that helps, but it's not going to do much.
Can you measure how much charge is pumped? You've got 3.
Nah, too complicated. Yeah. So what you do is, the electron positrons coming from the dark photon, they're special, because if you calculate their invariant mass, that's equal to the dark photon mass. Okay. So the momentum of the electron and the momentum of the positron, if you add them together and you square them, that's equal to the dark photon mass, right? Because we've got a diagram like this, That's an on-shell dark photon. Its mass is ma prime, right? Its momentum squared is ma prime squared, and that has to equal to the final momenta. And if you can measure the energy and momenta of the final state particles, you know that if you square them, you should get the dark photon mass.
And then you have to put in some knowledge or some guess for the mass to apply a cut, right? To reject the background. I mean, in principle, you don't know what you're looking for. So the only thing you can do is maybe a distribution and hope for a peak, but you cannot use it to cut away background.
No, but you can look for distribution, look for a peak. And you do a resonance search. Okay, very good. So what you do is you basically plot that variable. So this is often called the invariant mass. And you plot that distribution, and usually, depending on what electron positons you can collect, there's some finite range of momenta, etc., that you're actually accessible to. So an apex or so, it'll look something like this, some broad distribution. And then this is the number of events. So you plot all events, you get tons of events, and you just plot the invariant mass. The background is going to have some smooth distribution, hopefully smooth. And then what you're going to look for is you're going to look for a bump, a little resonance. Okay, and that's going to be the dark photon. Okay, and the better the mass resolution is, the more precise your momentum measurement is, and your energy measurement, the smaller this width is, because the natural width of the dark photon is tiny. It's a tiny width. There's a tiny width. Okay, so it's really this width of this particle in the data that you see is determined by the experimental resolution. How well you can measure the momentum, how well you can measure the energy. But that's what you're going to look for. And in reality, if you see something like this, that's very telling. Maybe it's going to be something like this. I can see it, but you can't. Okay. Okay, so it's going to be super tiny. But you can do, and then of course what you want is a lot of statistics, because the more statistics you have, the better idea you have on what the distribution is. And what you do at the end, you just take the signal prediction, which you can calculate from the theory, divided by the square root of the background. That's going to be your sensitivity. And you just take a tiny little bin. So you divide up the data, and you just scan for bumps across it. That's how the Higgs was found in gamma gamma. Okay, but there, of course, you could see it by eye. It'd be fantastic if we could see something like this by eye, but you can just do it automatically with code. There was a hand up somewhere.
Yeah. So I was just wondering how you get this factorization between the production and decay mechanism. If the width is small, then you clearly can't use the narrow width approximation. So how do you get that A prime on shell?
Well, if the width is small, I can use the narrow width, but basically,
I was thinking the other way.
Yeah. So basically, yeah, I can think of it as an on-shell thing being produced, living for a tiny fraction, and then decaying.
Sure.
Assuming there's such a peak is measured, can you then say for sure that it's this dark photon?
That's a fantastic problem to have. So I think, sure, you would want to then check the couplings. Does it decay to E plus E minus, mu plus E minus? How is the different strengths? That depends on the mass. Maybe it's below the muon threshold, then it'll just go to E plus E minus. You want to check the production cross-section. Ideally, then you want to find it in other experiments as well. Yeah, I mean, there's lots of cross-checks that you would need to do to know it's a dark photon. But finding something, okay. Yeah. Okay. Other questions? All right. Okay. Very good. Okay, so then the next point that someone said, so instead of prompt decays, you might want to look for displaced decays. Oh, let me just make one other point. So there's a paper that came out today, or yesterday, I saw in the archive today, it was either yesterday or today, which points out another way that you can produce the dark photons here. And in particular, they said that if the electrons interact with the target nuclei, then what you do is you actually also produce positrons in that beam. Okay, so there's just positron production from these kinds of processes. So if you have a very thick target, as the electron goes through your target, you actually start producing positrons as well. Right? And those positrons can interact with atomic electrons inside the target in a diagram just like what we have for E plus E minus colliders. and you can produce a dark photon like this. Okay. Or it could interact with, on resonance, I think you were asking this question on resonance. So if you produce these positrons in the beam dump, those positrons can also interact with electrons, and assuming, depending on the energy conditions, you can produce a dark photon like that as well. Okay. So this is just from the positrons that then get produced in this. And again, because I was giving you some papers from 2009, there was a paper today, or yesterday, that was pointing this out. It's actually an old idea, I think, but they actually did a careful analysis of it and also found some new constraints using that idea on dark photons. There were a lot of authors. I have the reference. Let me not mention one. I know some authors, but I don't want to mention anyone because I'm going to offend the others that I forgot. Here we go. Okay. Okay, so then, displace decays. So someone already mentioned this. So let's say you produce a dark photon and it decays. It has some little bit of a lifetime before it decays. In that case, what you want to do is you want to measure, you want to look for displace decay, so which is basically a decay, an electron-positron pair appearing in the middle of nowhere. And since the background is not expected to do that, you have a good way of looking for rejecting backgrounds. So here's your target, and the dark photon will be produced, and then decay to E plus E minus. And you can't see the dark photon, so what you have is just this E plus E minus pair appearing out of nowhere. Okay, and there's an experiment called the Heavy Photon Search, HPS, which has already taken some data, and will take more data next year. Also an experiment at Jefferson Lab. But what you do need to do is you need to track the electron-positron pairs coming out. So what they have is silicon tracking elements where there's a very nice vertex detector that measures the momentum of the electron-positrons coming out and then traces the momentum back and finds the origin of them and then sees if there's a displaced vertex. And you have to worry about multiple scattering of the positrons and electrons inside here, which degrades how well you can target this vertex. And there's, of course, a lot of background events still. So QED, these events, they still exist. They all originate here, but if there's some multiple scattering in the target or in the silicon tracking elements, that could mess up that could mess up where exactly the that's going to degrade the resolution of your vertex. So you have to worry about this a little bit. But anyway, so I'm making it sound very simple. It's not. So with a lot of work, you can do a great experiment here. Okay. And notice that I left this gap here because if you don't leave a gap, there's an electron beam going straight through, which is going to kill everything. Okay. And then finally, you want to have experiments that look for very long-lived dark photons. So those have decay lengths 1 to 100 meters or even more. It gets harder to do if it's much more. In that case, there's experiments that you can do where you've got a target, and then you can have a lot of shielding behind it, and then at some point you put a detector. And this could be, order hundreds of meters. And the electron's going to come in, hit stuff. The electron's going to come in, produce the dark photon. The dark photon doesn't care about the shield, etc. And then you want to look for dark photons decaying to E plus E minus in the detector. And of course, you've got to take into account the geometric effects. What's the chance of the E plus E minus decaying exactly here, and things like that. But there was an experiment that was done at SLAC in the 1980s called E137, which essentially, they didn't look for dark photons. Dark photons weren't popular back then. They looked for axions. But they were sensitive to dark photons as well. Okay, questions on that? Okay. Then, let me keep going through the different ways to produce dark photons. So, if you're able to produce mesons, mesons are a great source of dark photons. I think I'm numbering things, right? So I'm number 3. So meson decays are a great source of dark photons. So in particular, we can consider pi 0 going to gamma A prime, or phi going to eta A prime. And again, what you can do is wherever you've got a particle, like a pi 0, that is able to decay to 2 photons, you can replace one of these photons and make it a dark photon. And the branching ratio, or the width for the pion to decay to gamma A prime, divided by the width of pion going to gamma gamma, is going to be given by 2 epsilon squared, apologies for the writing this on the side, 1 minus ma prime over m pi. This must be squared. Okay. Okay, so wherever you have a meson that decays to photons, or your photon is something else, you could have a chance of having a dark photon produced in that decay. And the mass range of dark photons that you can then probe, of course, is limited by, for the pion, it's limited by the pion mass. And for the phi, it's limited by phi minus eta mass. But there's some window of dark photons you can produce in this. And the branching ratio, or the ratio of the widths of the gamma A prime to the gamma gamma is obviously has to depend on epsilon squared. There's a factor of 2 because there's A prime, I can put it here or there. Okay, whereas the gamma gamma, it's invariant. There's a symmetry factor there. And then there's some mass dependence, mass threshold. Now, where do you produce where do you produce mesons? You produce them in many different places. Chloe was a great source of phi mesons. Okay, so Chloe was able to do a search like this, and they've done a search like this. Pions get produced all over the place. Even at Brookhaven National Lab, at RIC, which is a heavy ion collider, they got a detector called Phoenix, and they produce a lot of pions, and they did a search for this channel here. Pions also get produced, so based in E plus E minus colliders, like B factories or phi factories, you can produce these things. And another great way of producing them are proton fixed target experiments. So let me just write this. So how mesons are produced, e.g. at E plus E minus colliders, at RIC, relativistic heavy ion collider, that's what RIC means. And then at proton beam dumps, which I will talk about next.
Is much smaller than this. So phi level, you just use electron.
It actually depends a little bit. So you actually produce a lot of phi mesons. Like Chloe, right? It's sitting right on the resonance. So they're maximizing the phi production. They're tuning the beam energy to be right on resonance on the phi. So they're producing a ton of phis. At RIC, you've got proton-proton collisions or heavy ion collisions, which will also produce lots of pions. So there's no electron beam there. There's just, you could get mesons and all kinds of a big mess, but you get a lot of pions. So you can do that search as well. So depending on what search is better depends a little bit. So at Baba, the E plus E minus search was better, not the meson search. Okay. But at proton fixed target experiments, which I'll label as number 4, so this was first pointed out in a paper back in 2009 as well. So there the idea is that instead of taking an electron beam, you've got a proton beam on a target. And then in that interaction, you produce a lot of mesons, pions, pi plus, pi minus, pi 0. But the pions are interesting. Those pions will decay to gamma, which you don't care about, and the dark photon. And then the dark photon can, again, depending on how long-lived it is, it can keep moving. And then you want to put a detector somewhere. And then the dark photon can decay to E plus E minus. Okay. Now, this kind of setup where you shoot a proton beam on a target, what does it remind you of? Who does that? Why would you do that? Who does that? I didn't hear. And who said something? LHCb? Well, that's proton-proton collisions. Okay. But there are other facilities that do that. Who works on neutrinos? Yeah, okay. Okay, good. So one person knows because they work on neutrinos. Good. So that's how you produce neutrinos. Okay, that's one way to produce neutrinos. A very good way. So in particular, the way neutrinos get produced at Fermilab in Japan, in various places, is that you take a proton beam, you shoot it onto a target, and you produce mesons. So there, what you care about are pi plus or minuses. Those tend to decay to mu plus or minus and muon neutrinos, with or without a bar, depending on the sign of which one it is. And then the neutrinos will happily go along, and then they will interact with the detector far away. Okay, but you can use the same setup to look for dark photons. Okay, and the experiments that are relevant, right, are based on neutrino facilities in general, but not just. Well, okay, so there's various neutrino facilities. So LS&D, which was the 1990s. I forget when it stopped running, but it was around that time there. And then mini boon. There's always the question about what's capital, what's not. I think this is correct. There's SHIP, which is a proposed experiment at LHC. Okay, at CERN, I should say. So that's a proton beam fixed target. There's Sequest, which is an experiment at Fermilab, proton beam. And there's others. Okay, so basically, this is just EG. Okay. So June, future things, T2K. Okay. And the number of dark photons that you get here is roughly determined by the number of pions you get. And very roughly, the number of pions you get is, about for each proton that you dump, you very roughly get a pion. And then, of course, how many A primes, how many dark photons you get depends on the epsilon. Okay, and the epsilon needs to be reasonably small because you want to make sure the dark photon is long-lived, because usually the detectors are quite far away. Okay. All right. Let me mention a few other things very quickly. So there's rare Higgs decays at the LHC. That's not a great source, but it's a fun source because it's the Higgs. So remember that this morning, someone even asked this, but this morning what I said was that the dark photon, the dark U1, is actually mixing with the hypercharge, not with the photon itself. So it's mixing with hypercharge. So there's some small mixing with a Z. And just like the Higgs can go to ZZ, you can actually have a small decay of ZA prime. Okay, and that's a rare decay of the Higgs. So if the dark photon exists, you can look for this. And there's constraints already, and that allows you to go to quite large masses, A prime masses, because the Higgs, of course, is 125 GeV, heavier than the other things that we're talking about here. Okay, so that's one way to do this, and one reference for this is this one here. Okay, then, yeah, I should mention at least this. So there's other things that I'm not going to mention, but there's one thing that I do want to mention still here. So at the LHC, or in principle also at other facilities, but the LHC is a great one right now. Another way to produce the dark photon is just from proton-proton collisions. So this is proton-proton collisions going to dark photon plus whatever, okay, something else. Okay, it's an inclusive process. And then there's actually several experiments which are going to try and look for this process. So there's LHCb, which has excellent tracking and which can do a very nice search. They already actually published some results. And there's other experiments that have been proposed, like PHASER. So PHASER stands for Forward Search Experiment. You have to take letters from the middle of the word to make the acronym PHASER. So Forward Search Experiment. Okay. There's the combat detection, Codex B, which is combat detection for exotics. That's actually a detector that people are proposing to be close to the LHCb detector. Okay, that stands for compact detection for exotics at LHCb. So it's a separate detector near the LHCb detector. So basically you would put some shielding between the interaction point and the Codex B detector. And there's experiments like, so in principle also Methuselah, which can look for dark photons and other things, which is a detector on the surface, proposed detector on the surface of the LHC. So this is 100 meters above the LHC tunnel. So the LHC tunnel is 100 meters underground. On the surface, you can people are imagining putting a detector called Methuselah, which stands for Massive Timing Hodoscope for Ultra-Stable Neutral Particles, where you would look for very long-lived particles that get produced at the LHC and then make it out all the way to the surface. Okay. All these three here, I should say, they are detectors to look for long-lived particles. And they're all experiments that have been proposed to be done. Okay, order million scale and more. Okay. And they're sort of to show, and these are all pretty recent things over the last year or two that people have developed. So there's a lot of activity in terms of coming up with new ideas. And the dark photon model is just one example, right? I focused on this because I have to focus on something just to get through lectures here, final amount of lectures. But you can imagine more complicated dark sectors where you can produce particles, where these experiments can do a lot of interesting physics and a lot of searches for dark sectors. Okay. Yeah, so PHASER, for example, is an experiment that's 480 meters away from the interaction point in the atlas. So there's a little tunnel, and there's a little side passage, and then I want to put a little detector there, which would then, where proton-protons collide at atlas, they would then be able to produce particles there and have it go to the detector. Okay. And the dark photon could be produced there, and they cage E plus E minus or mu plus E minus in the detector. Okay, so there's lots of stuff. I think I want to stop there and mention one final thing. So back in 2008, when dark photons became popular, so again, they've been around for a long time. They were first proposed by Hold'em and Gallison and Manoa in the 80s. And then, if you look at the citations to Hold'em's paper, sort of order 10-ish for a long, long time, and then 2008 it jumps to 100 per year. Okay, so lots of citations, a lot of activity since then. But one of the things that was interesting is that this is not a different production, but maybe another motivation for dark photons is that you could explain anomalies in the mu and anomalous magnetic moment. Okay, let me explain this a little bit. So every charged particle has a magnetic, and that has a non-zero spin, has a magnetic moment, okay, magnetic dipole moment. And that magnetic dipole moment is proportional to the spin of the particle and the proportionality factor is some G sub S here, and there's a charge and a mass that depends on of the particle, and then the spin. Okay, so this is the spin. Let's take the electron, then that's the spin of the electron, that's the charge of the electron, mass of the electron, and there's some proportionality factor. Same for the muon, same for other particles. And this can be calculated what it should be. And the diagram that does this calculation is basically this diagram here. And back in the 1930s, the answer that you get from what this contribution should be is that at leading order, at tree level, so this, let's take the muon, the G should be 2, okay, at tree level. Now, of course, it's not 2 because there's corrections. Corrections come in many different forms. There's corrections like this from a photon. There's there's various corrections, and that means that it differs from 2 a little bit. And the amount it differs from 2 is called anomalous magnetic moment. I think it's defined to be divided by 2 as well. All right, and the leading order contribution is actually from a photon, and you can calculate this diagram, and this is going to be given by alpha over 2 pi. And this is a calculation that you probably did in field theory, okay? And Michael has it in his book, of course. So it turns out, so you can measure this, and you can also calculate it. And it turns out that for the muon, there's a discrepancy between the measured value and the calculated value. The calculation is not trivial, because the calculation involves diagrams that are, for example, photon-photon with hadrons in here. And we're sitting at low energies, and it's hard to do calculations in QCD at low energies and have control of them. So there's various ways to try and understand this, and there's calculations going on in lattice QCD to try and actually calculate this from first principles. But the calculation is complicated, but nevertheless, people do, experts, not me, do a great job at doing this calculation. There's a discrepancy between that and the measured value. And for the muon, it sits at about 3.6 sigma. So that's a long-standing discrepancy, which is more a reflection of the fact that it's taking a long time to get more data. So this was a measurement done at Brookhaven National Lab, 2000-ish something. Maybe someone else knows more precise date, but it was a long time ago. And now there's a new effort underway at Fermilab to redo this measurement more precisely. But nevertheless, there's a discrepancy. And it turns out that a dark photon can explain this discrepancy by a very simple diagram. Same thing with a photon, but just put a dark photon there. Okay. And then there's an epsilon here, there's an epsilon there. And depending on the mass and the epsilon, you can actually get the right answer. So for a dark photon, I'm using my old writing just to add for the dark photon now. So it's times 1 for a dark photon mass much less than the muon, and it's times 2 mu squared over 3 ma prime squared for ma prime much larger than mu. Okay, so for dark photon mass very light to muon, it's basically just like a photon except with an epsilon squared correction, right? Because it's the same diagram. But once the dark photon mass becomes larger than the muon mass, you need to take that into account, and there's some correction. But nevertheless, you can actually do that calculation, and it works, right? So you can actually use a dark photon to explain this discrepancy. So back in until a few years ago, this was a big motivation to look for dark photons. And back in 2008, I'm now going to draw you the plot of the dark photon and the epsilon parameter space. I'm going to do this by hand because I'm very skilled. So there's going to be epsilon on the y-axis and the dark photon mass. I'm going to start at 1 MeV. That's the region we focused on. I'm going to cut the plot off at 10 to the minus 2. And back in 2008, we had a rough bound. Wait, before I do that. So here's 10 to the minus 4. So if you wanted to explain this muon G minus 2 anomaly, you want it to live somewhere here. This is going to go wrong. Okay. So it was a pretty sharp prediction. Okay. So this is 1 MeV, that's an epsilon of 10 to the minus 3 on this axis here. And so that's the A minus, this is the muon G minus 2 preferred region. Now at the same time, you can ask the same question about the G minus 2 of the electron. Oh, okay, okay, good. And there, unfortunately, the situation is the opposite. So there's also actually, this is a very recent measurement that was done with cesium-133 atoms in a matter wave interferometer by Holger Müller and company in Berkeley. They did a measurement of alpha, the fine structure constant. I think that's the most precise measurement, more precise than G minus 2 of the electron, I think, now for the first time. And they find actually discrepancy that for the muon G minus, for the electron G minus 2, there's a 2.5 sigma tension, so it goes the opposite way. So the dark photon contribution has a certain sign. For the muon, it goes the right way. For the electron, it goes the wrong way. So there's a small discrepancy also for the electron. And if you add a dark photon, it makes the discrepancy worse. Okay. So that sets a bound, and right now that bound, I'm not going to draw this accurately. You can look at plots. But basically, I don't know, something like this. Okay. So this is roughly the bound from G minus 2 of the electron. So in this cosmic visions paper, the reference that I gave in the first lecture, you can look at and see more professional plots. But roughly this, so back in 2008, this was not as stringent, but it was a bit weaker. But nevertheless, the situation was roughly similar. Okay, this was the bound. And then people started talking about all these different experiments that could be done, and different searches started happening. And then the situation today is roughly as follows. So we've got beam dump experiments that are exploring parameter space like this, which is all excluded. There's bounds that actually come from supernova cooling, which I'm not going to explain. I'll just mention it briefly, which exclude. This is from supernovas. This is from beam dumps, like E137, right? These long-lived things, E137, for example. There's others that I didn't mention. And then up here, there were lots of searches done by Baba, by Chloe, by Mainz, right? By Mami here in Mainz, where they excluded this explanation. The muon G minus 2 has the dark photon explanation of the muon G minus 2 is basically excluded now. So very roughly, this is the bound, and it goes up to about a GeV, and then actually about 10 GeV from Baba. So setting up here are constraints from Baba, Mami, Apex a little bit, Chloe, etc., etc. Okay, and then above 10 GeV, there's the LHC bounds that come in from like the Higgs decay, for example, and something else that I also didn't mention. But that's roughly what you get. So what you have right now is that there's still open parameter space. So roughly, there's various beam dumps here. So there's still open parameter space here that's not explored. And of course, there's lots of open parameter space here that's not explored. Just turns out that below GeV, it's easier to explore. But there's new experiments being planned, right, that I mentioned. So this will be covered by new experiments over the next 5 years or so, to a large extent. So HBS, LHCb, Apex, etc. Okay, so that's a lot of effort for one simple model. But it's a very simple dark sector, which is the building block of many things. So this is good. Okay, questions on this? Yeah.
I didn't understand. Did they already cover this intersection of the muon and electron G minus 2?
Right, so this is basically ruled out. So dark photons decaying visibly directed to standard model particles is basically disfavored as an explanation for the muon G-2 anomaly. So these experiments that are still going on, they're just going to cover parameter space because, you know, maybe dark matter interacts with dark photons, or yeah, just because it's an interesting dark sector mediator.
What Michael said yesterday about whack-a-mole. You fix the muon G-2 and you have a problem with the electron G-2.
Yeah. So the electron G-2 is interesting because there's just a tension within the standard model, if you like, 2.5 sigma. It's not clear what the resolution is.
But I understood the electron G-2 to like agree QFT and experiment out to 10 to the -10. Am I just wrong about that? I thought it was the best tested.
You mean 10? Say again? Yeah.
To like 10 to
like 10 significant figures?
Yes.
Yeah, it's fantastic. We're talking about super precise things.
Wow.
Yeah. Okay. I've got 5 minutes. I'm going to use them. Okay, so what I want to do now, and I'll do this quicker than did the other stuff, is I want to bring back the idea that the dark matter is there and make it light. And instead of having the dark photon decay to standard model particles, so E plus E minus, mu plus E minus, I want to have it decay to dark matter. Okay, so now make the dark matter light, and in particular, make the dark matter lighter than half the A prime mass. Okay, so in the opposite limit, the dark photon, when it's produced, will decay to standard model particles. But if you've got very light dark matter particles sitting around, then the dark photon will decay to some new state, some invisible state, invisible to your detector, because it's very difficult to see the dark matter. But we'll talk about how we can identify it. Okay, so you want to make the dark photon heavy compared to the dark matter. And then this drastically changes the phonology. And just to show you, so I'm going to mention a few things now, go through some of these lists and see how you can still look now for these light dark matter particles. And this allows you to probe low mass dark matter with beam dumps or with fixed target experiments. So again, you've got many searches possible. So going back to our E plus E minus colliders, you can use a technique called missing mass. So here's the same diagram again. I'm producing my gamma gamma, and sometimes a gamma A prime. And now the A prime is produced and will decay to chi chi. Right, so it's produced on shell and then decays to chi chi. Or chi chi bar if it's a fermion, right? So I'm being a bit careless about this. So what do you see? What you see is gamma plus nothing, because you can't detect the dark matter directly in the interaction in the detector. Now, as before, the production cross-section is the same cross-section that I wrote down before. I'm not going to write it down again. So it depends on one of the center mass energy squared. So you produce a lot of these. But now what do? You have to look for gamma plus nothing. So what you're looking for is basically a single photon event. But this dark photon has a specific mass. So you're actually looking for a monochromatic photon. So a photon with a specific energy. So if you know the incoming beam energies, as you do in a collider, then you're basically going to produce a monochromatic photon. And then you can measure this and you can plot the following quantity. So instead of plotting the invariant mass of E plus E minus, which you don't have now, what you do is you plot the quantity, which I'm here calling mx squared. And you're plotting events as mx squared. And mx squared is defined to be the center of mass energy squared, S, minus 2 times the measured photon energy, times root of S. And you can calculate this. You can just do the kinematic calculation as an exercise. That is basically going to be the dark photon mass squared. Okay. So you plot this. There's, of course, background again. But without background, what you would expect to see is this. And if there's backgrounds, right, this will be a bump on some background. Okay, so that's what the signal is that you're looking for in MA prime, like this. And this is called, so you plot this missing mass that's defined here, and you look for a missing mass peak on top of some background. And of course, what you want is you want to again have very good energy resolution, because the better your energy resolution is for the photon, the more precise you know what the width of this is, right? So the photon energy, whenever you measure the photon energy, if it comes from if the dark photon is being produced with it, the E gamma is exactly known. But since there's uncertainty in measuring it, I'm drawing some finite width here. Okay. And then there's, so this search was actually done at Babar. Or first it was done using public Babar data. And then they did it themselves. And there's an existing constraint from Babar that was done in 2017, so not that long ago. And future experiments, they're going to include Bell 2 and PADME. So I'm going to write down these names once so you have seen them. So, well, I'll just say in words. So PADME is a positron beam use a positron beam on a diamond target. There's MMAPS. I don't know what all these things stand for anymore, I forget. So PADME is an experiment in Italy. MMAPS is an experiment at Cornell, proposed experiment. This is a positron beam on a beryllium target. Then there is VEP3, which is an experiment in Russia at the Budka Institute, which is a positron beam on a hydrogen target. And there's also dark light, which is an experiment at Jefferson Lab in the US, where it's an electron beam on a hydrogen target as well. So lots of different experiments proposed to look for this particular thing. Okay. And this is not an easy search to do, because at Babar, for example, we needed to see monophoton events. And it turns out those are very difficult to collect without being swamped by background. And in addition, they actually only had a single photon triggered by Babar for a tiny fraction of the data. So for only about 30 inverse femtobarn or 50 inverse femtobarn of the data, out of 500 total events collected, inverse femtobarn of data collected, they had this single photon trigger. So only a small amount of data was analyzed there. And Bell 2, my understanding is they're working very hard to have a single photon trigger, and I hope they'll be successful, but we'll see. Okay. Okay, I'll stop here, otherwise I get in trouble. So we'll continue tomorrow morning. I'll have 10 more minutes on these searches for accelerator-based things, then I'll turn into new direct detection searches below the GeV scale. And I'll tell you a little bit of what's going on there. Thanks.